Right, heat transfer question. We have a house and we have a rectangular duct. So we have hot air enters at 85°C, 10 meter long. And so this is a cross section 15 by 15, so it's square, at a rate of 0.1 meter cubed per second. So that's V dot, volumetric flow rate. We want exit temperature, T2, and 75°C. So that's what this table is. It's just a bunch of information at air at 75°C. So because this is a square duct, the first thing we need to do, calculate the hydraulic diameter. So that's basically the diameter that we would expect this to be if instead of a square, it was a circle. So the formula for that is 4AC over P. So if we call the length of the square L, the cross-sectional area is L squared, area squared. The perimeter of the square is 4 L's. So 4L. So an L gets canceled out and the 4's get canceled out. We're left with the diameter, the length L, which is 0.15 meters. So now we need the velocity to get the Reynolds number, which is the big first thing we need to do. So the velocity is the volume flow rate divided by the cross-sectional area, which the volume flow rate over here, 0.1, cross-sectional area, 0.15 squared. So the velocity is 4.4 meters per second. Okay, now we see the random number. And that's VD over kinematic viscosity. And we have all of these things. So 4.4 meters per second, the diameter, the hydraulic diameter, and the kinematic viscosity up here, 2.046 times 10 to the negative 5. So that gives Reynolds number 32584. So this Reynolds number is greater than the critical Reynolds value. It's greater than 10,000. So that means this is turbulent. Which means that we use the turbulent. From here we can calculate the Nusselt number, which is 0.023 times Reynolds number to the 0.8 times Prandtl to the 0.3. So we can substitute in 0.023 times 32584 to the 0.8 times the Prandtl number, which is 0.7166 to the 0.3. Calculating this, we get 84.86. And then we can solve for H. And that is KD times the Nusselt number. So we're given all of these things. So the hydraulic diameter, 0.15. .86. Calculate H. That is 16.5 watts per meter squared C. What are we looking for specifically? Exit temperature and the rate of heat loss. Okay, so that's Q dot and TE. Well, I know that TE is the surface temperature minus the difference in temperature between the surface and the inlet times E to the negative HA M dot CP. So now we need M dot and we need AS. So we have a rectangular duct. The surface area is just going to be all of these surfaces added together. So if this is L and this was this L, curly L, the surface area is L times L times 4 because there's 4 faces. Which is 4 times 0.15 times 10, which is equal to 6 meters squared. We also need M dot. That's just rho V dot. So 1.014 times 0.1 is 0.1014 kilogram per second. So now we have everything we can plug in to this equation. So surface temperature 70 minus 70 minus 85 exponential negative H 16.5 times AC, AS is 0.6 0.1014 times CP. What was CP? 1007.5. Type all of this into the calculator. We get that TE is 75.69 degrees C. Nice. So that's part A. Now we need Q dot. To do that, we need the log mean temperature. Delta T log mean. This is just so we can estimate the effectively average temperature between these 3 temperatures. So we have all of these values. 75.69, nice, minus 85, ln 70 minus 70.69, nice, 70 minus 85. So we type this into our calculator. We get that the average temperature is 9.604. So the average temperature distance is about 9.64, which kind of makes sense. This is about 10, and this is about 15, so it should be in that ballpark. and then the temperature difference between 70 and 75 is 5. So between 5 and 15, 9.6, it kind of makes sense. So now we just need to calculate Q dot as HAS delta T. So 16.5, 6, 9.604. We have all of these. Q dot is 951 watts. Bang.